Okay, let's refresh our memory as to what we were talking about in terms of MLE and MAP. These are two techniques where we can estimate the value of parameters in our Bayes classifiers. So MLE is what we were discussing first. It stands for maximum likelihood estimation. And the equation here is suggesting that the optimal estimate for any parameter, let's call it theta, is the argument theta that maximizes some probability. It's the probability of seeing the data that we have given the value of the parameter. Okay, and I just want to be clear, this is completely separate from the idea of the posterior probabilities that we use in the Bayes classifiers. This is just another representation for how we could determine what any of the probabilities in a Bayes classifier is using the data that were provided. Okay, and then we made this note off to the side here that we can take the natural log of this probability of d given theta. We refer to this as the log likelihood. And the reason why this is okay or mathematically sound is because the natural log is monotonic. So if some value a is greater than b, then the natural log of a is also greater than the natural log of b. This is a technique that has come up or should come up in your Bayes classifier itself in terms of making the arithmetic, the scale of the values more reasonable. A couple other notes that we made are that here the data is independent and identically distributed. So we call that IID for short. It means that each sample in our data is independent of the next one and they're coming from the same underlying distribution. The parameter that we care about, we're assuming that it's fixed but that it's unknown. And this form of estimation will converge the more data we have. Okay, and then we were starting to work through this example of estimating the probability of flipping heads. So we said here that the data D is all of the coin flips. So we have D1, D2, up to DK. Okay, and theta, the parameter we care about, is the probability of flipping heads. Without loss of generality, we could have defined theta as the probability of flipping tails. The important distinction here is that if we define theta as being heads, then tails is simply 1 minus theta, right? Those probabilities have to sum to 1 based on the axioms of probability. Okay, and then because these are independent and identically distributed, we can change that conditional probability, which involves the joint distribution of all the data, all of the coin flips, into the product of the individual conditional probabilities. So we have P of D sub I given theta here. What's the probability of one of the coin flips given some value for theta? So if we have in our data set, let's say alpha H, number of times that we flipped heads, and alpha T, number of times that we flipped tails, this expression simplifies to theta to the alpha H times 1 minus theta to the alpha T. Now, we haven't quite done the log yet, so that's where we need to go now. To compute the log likelihood, I'm going to define this as L, kind of this fancy cursive L here. The log likelihood of a given parameter theta is going to be equal to the natural log of that probability that we just saw, d given theta. So we already have an expression for that probability, so we can write the natural log of theta to the alpha h times 1 minus theta to the alpha t. If you're not as familiar with the natural log, one of the nice properties of logs is that if we take the natural log of, let's say, x times y, that can be rewritten as the sum of the logs of x and y individually. So I hope you see where I'm going here. This expression over here can now be written as the log of theta to the alpha h plus the log of 1 minus theta to the alpha t. Another nice property of logs is that if we have, for instance, the log of x to the power of y, we can rewrite this as y times the natural log of x. So over here on the right here, these are just properties of the natural logarithm. So with this knowledge, we can bring those exponents down. We have alpha h times the natural log of theta plus alpha t times the natural log of 1 minus theta. The goal here is to maximize this expression. In order to maximize some function, we simply set the derivative equal to 0 and solve for the unknown parameter. So let's do that here. If we take the derivative of the log likelihood with respect to theta, now this, I probably should have written this in this blue box to the side. The derivative of the natural log of some variable x is equal to 1 over x. So here, this alpha h is just a multiplicative factor here. But the derivative of the log of theta is 1 over theta. And then similarly for alpha t, the derivative of the log of 1 minus theta is actually negative 1 over 1 minus theta. Okay, and then we need to set this all equal to 0. So the goal here is now to solve for theta. I can move some terms to the other side. Then we can cross multiply, distributing the alpha h in, moving the alpha h theta to the left side, combining those terms, and then dividing both sides by that term in parentheses gives us the final estimate. So the final estimate of theta, which remember, theta here stands for the probability of seeing heads, it is simply equal to the number of times that we flipped heads divided by the total number of flips. Notice that the total number of flips here is represented by alpha h plus alpha t. Right? That will equal k in this case. Okay, let's try a slightly more challenging problem. Dice rolling. Suppose we have a 6-sided die, and our goal is to guess what we're going to roll next. Now, within that goal, let's define some important probabilities. So suppose I say that the parameter theta 1 is going to be defined as the probability that y equals 1. Theta 2 is the probability that y equals 2. Theta 3, probability that y equals 3, all the way down to theta 6, probability that y equals 6. And this example would apply no matter how many sides of our die there are. You should notice that if we were to sum all of these parameters, theta sub I from I equals 1 to 6, by the axioms of probability, that should equal 1. Okay, now, what is maximum likelihood estimation suggesting? It's suggesting that we now have potentially a vector of estimated parameters. I know this is kind of a weird notation. I'm just implying that we could have an estimate for each of the theta parameters, and I'm going to set that equal to the argmax for that array or vector of theta values of the natural log of the probability of d given the values for those parameters. And just keep in mind, this right here is what we refer to as the log likelihood. Now, in order to solve for this equation, we need to first understand what that probability, d given theta as an array, is equal to. Well, because of our assumption of independent and identically distributed data samples, we can separate out that conditional probability to each of its parts. So here k is referring to the number of data samples we have, and lowercase d sub I is one of those samples, so one of the dice rolls. Now, we've already defined each of the theta parameters, theta 1 through theta 6, so the probability of seeing a roll of 2, given a certain probability of rolls of 1, 2, 3, 4, 5, 6, is simply going to be equal to theta 2. So just like in the flipping coins problem, this equation will simplify to a product of each of the theta 1, theta 2, theta 3, all the way up to theta 6, but they're all going to have exponents. Those exponents refer to the number of times in the data set that we saw those examples. If that doesn't make sense, you could think about writing this whole multiplication expression out individually. You know, if we rolled a 3 first, it would be theta 3 times maybe theta 4 for rolling a 4, then theta 6, then theta 3 again, then theta 1, then theta 2. We're just trying to combine all of those terms to simplify the expression. Once we've done that, we can now compute the log likelihood as before. So the log likelihood for our array of parameters theta is equal to the log of the probability of d given theta. And I'm going to skip a couple steps here from the math on the previous example and just say that this is equal to alpha 1, the number of times that we rolled a 1, times the log of theta 1, plus alpha 2 times the log of theta 2, plus so on and so forth, all the way up to alpha 6 times the log of theta 6. Now here's the tricky part. How do we solve for all of those thetas simultaneously? So we have to take derivatives again and set them equal to 0. But the derivative here is actually something that we call the gradient. So we would say the gradient of that log likelihood is equal to an array. So that array is each of the individual derivatives. So derivative of L with respect to theta 1, derivative with respect to theta 2, all the way down to the derivative with respect to theta 6. So what's nice about this is that we can consider each of these variables independently. So I want to make a note here that the expression above with the alphas and all the thetas, note that this is also equal alpha 1 natural log of theta 1 plus we can actually add all of the other alphas together and multiply this times the log of 1 minus theta 1. So in other words, we're kind of turning this problem where we have multiple outcomes into two outcomes. Either it was we rolled a 1 or we didn't. How many times did we not roll a 1? Well, it's alpha 2 plus alpha 3, alpha 4, alpha 5, alpha 6. Okay, the reason we can simplify it in that way is because now it makes our derivative a little bit more manageable. So we can write this derivative as alpha 1 divided by theta 1. Again, these are just properties of the natural log. I don't necessarily expect that you've already learned this or had this memorized. Minus 1 over 1 minus theta 1 times the sum of alpha 2, alpha 3, and so on and so forth, up to alpha 6. We could also, let me show you what the equation for alpha 2 would look like. It's alpha 2, the derivative here, alpha 2 divided by theta 2 minus 1 over 1 minus alpha 2 times, in this case, it's alpha 1 plus alpha 3 plus alpha 4, alpha 5, alpha 6. So I hope you see that we're grouping all of the alphas that don't involve the parameter we care about, in each of the rows. And we're going to get 6 equations like that. I'm just going to put ... there because I think you see the pattern. And the goal here is to set all of those equations to 0. And then we should solve for the unknown parameter. So let me show you how we might solve. Let's do this from one of those examples. If we solve for theta 1, we can move the negative term to the right side. Then we can cross multiply, distributing the alpha 1 in on the right side, moving the theta 1 term to the left. So we move this over here. We can group the like terms, and now we have the sum of all of the numbers equal to alpha 1. Where does this leave us? This means that our estimate of theta 1 is equal to alpha 1, the number of times that we rolled a 1, divided by the sum of alpha 1, alpha 2, all the way to alpha 6. More generally, we can actually say that the estimate of any of our parameters, probably shouldn't use k here, is going to be equal to the number of times that we saw that particular instance divided by the sum of all of the alphas. Let's summarize. For maximum likelihood estimation, the calculus that we just did demonstrates that one way to estimate a parameter in a Bayes classifier that involves probabilities is simply to count the number of times that we saw that sample or that outcome in the data divided by all of the data instances. So in our homeworks, when we say something like, let's look at the maximum likelihood estimate for the prior probabilities of topics of sentences, we simply go through the training set, count the number of times that each topic happened, and divide it by the total number of sentences. That is what we just derived here with MLE. Okay, let's move on to the second one. So MAP refers to maximum a posteriori. And in this form, we are going to approximate the estimate of a parameter will be equal to the argmax again of that parameter. But this time it's going to be the probability of theta given d. Let's remind ourselves what each of these terms means. Now I hope you recognize that this looks very similar, like eerily similar, to MLE, and it should. However, it is different. We have swapped the theta and the d in that probability. And because of our knowledge of Bayes' rule, we know that this is proportional to the probability of d given theta times the probability of theta divided by the probability of d. Now here's the beauty of applying Bayes' rule here. We are trying to optimize for theta. When we look at the terms in orange, the one in the denominator doesn't involve theta. It's just saying what is the prior likelihood of seeing the data that we have. To be honest, the response is really like, who cares? It doesn't affect which theta is the best estimate here, right? It's just like a multiplicative factor that frankly makes sure all the probabilities follow the axioms that we care about. But if all we care about is finding the optimal theta, we can ignore the probability terms that don't involve theta. Okay, so we're going to solve for what's in the top, the numerator in orange, probability of d given theta times the probability of theta. Some notes, just like in the MLE case, we're going to assume IID data. The parameters here are now treated as random variables that have some known distribution. This is the difference. So MAP is similar to MLE, but now we have prior probabilities. And if it's not clear where that's coming from, let me highlight it. This is the prior probability. We're assuming that our parameter, theta, any of the parameters, that it's random, but we know the distribution it comes from. And we're going to incorporate that into our optimization here. To do that, we actually need to know which prior we're going to use. In other words, what is the p of theta? For binomial problems, we're going to use something called the beta distribution. So our prior probability of theta, any of our parameters, which here we're still going to keep with, notice the h and the t. This is assuming, for instance, that theta is defined as the probability of flipping heads. So we're using that coin flipping problem as just kind of the generic template for any binomial problem. Okay, and it's equal to theta to the power of beta h minus 1 times 1 minus theta to the power of beta t minus 1 divided by some factor. We just call it b. That's a function of beta h and beta t. If you really care about that, it's some really complicated integral. But the thing I want to highlight here on this slide are the beta h and beta t. These are like virtual coin flips. Now, allow me to draw what this distribution looks like in practice. So on the x-axis, we have the parameter we're trying to estimate, theta, and on the y-axis, we're showing the prior probability of seeing some value for that parameter. So in the red curve, I'm suggesting that there's an even number of virtual heads and tails. It should make sense that the peak of this curve is at 0.5 because we've added an equal number of both options. And so the most likely value of theta, the probability of flipping heads, should be 50%, 0.5. In the orange case, we have now skewed the data towards the virtual tails. So I'm saying we had 2 virtual heads, 5 virtual tails, and now the maximum of this curve has shifted to the left. In other words, with this prior distribution, it is less likely that we are going to flip heads. And then you can see as we increase the number of virtual counts, even if I kept that same ratio, in the blue, you'll see that that curve has now become a lot more narrow. So the more data we have in this beta distribution, essentially the more certain we are that the true probability should be, in this case, somewhere less than 0.5. So that's just to demonstrate the distribution that we often will assume. But now we can apply that distribution to the problem of solving for the map estimate. Let's do that together. Okay, so let's remind ourselves of the equation we're worried about. The estimate of our parameter theta is going to be equal to the argmax of theta of the probability of seeing theta given the data set that we have. And we already said, based on Bayes' rule, this is proportional to the probability of our data given theta times the prior probability of theta. Okay, remember we got rid of the denominator term, probability of seeing our data d, because it has nothing to do with the parameter that we're optimizing. So some terminology here, we can refer to that part on the left as the posterior. The first term on the right here is our likelihood. And then the last term here, what makes map different from MLE is that we have this prior distribution. In terms of solving for the equation on the right, you might recall that we've already done the likelihood part. That's theta to the power of alpha h, the number of times that we saw heads, times 1 minus theta to the alpha t, the number of times that we saw tails. For the prior, we just defined or assumed that we would use the beta distribution. So let me remind you of that equation. So therefore, the posterior probability of theta given d, that's going to be equal to the product of these two terms. Notice that we're going to have multiple terms that have theta, multiple terms with 1 minus theta. So let's combine those exponents. All divided by this factor that we call the beta function that is based on the virtual counts here. I hope you'll notice that this denominator, just like P of D in Bayes' rule, got ignored because it had nothing to do with theta. If you look at this beta term, or the beta function B of beta h beta t, that also does not depend on theta. So we ignore it. So we're left with just the term in the numerator. How do we solve for theta? Well, we do the log likelihood, take the derivative, and set it equal to 0. So let's write out the log likelihood of that parameter theta is now equal to the log of the probability of theta given d, which equals, I'm already going to bring the exponents down. That will be alpha h plus beta h minus 1 times the log of theta plus alpha t plus beta t minus 1 times the log of 1 minus theta. Right, so I already moved all the exponents down and I separated the product into the sum. Now I can take the derivative of L with respect to theta. That's going to be equal to alpha h plus beta h minus 1 divided by theta for that first term, minus alpha t plus beta t minus 1 over 1 minus theta for the second term. I set it equal to 0 because we want to find the maximum. If I move the term on the right, the negative term, to the right side of the expression, we're left with alpha h plus beta h minus 1 over theta equals alpha t plus beta t minus 1 divided by 1 minus theta. And I think you're seeing a pattern here. We can then do the cross multiplication. I'm going to save a step here on the slides, but hopefully you can see how we can distribute that term in parentheses on the right into the 1 minus theta and move the theta terms to the same side. So let's try that. Okay, and now solving for the estimate of theta by dividing both sides by that term in parentheses, we have, okay, this is our final result. I want you to think about what this result is suggesting for the case of flipping coins and determining the likelihood of seeing heads. The likelihood of seeing heads is equal to the number of times we actually saw heads, that's alpha h, plus our virtual counts of heads, beta h minus 1, divided by the sum of our actual data, that's the alpha t plus alpha h, and the sum of our virtual data. Now those minus 1s everywhere is due to the definition of the beta distribution. I realize that that can be unsettling. So let me show you one thing that is common to do at this point. And that's to say, if we let beta h be equal to beta t, so typically we'll have the virtual counts be the same. We're not trying to bias the classifier one way or the other. And we often will set that to some expression 1 plus c. So c here is a constant, or maybe it's better. You know what? In fact, for this example, I'm going to say 1 plus beta so that we still see the betas. So we're letting the number of virtual heads and virtual tails both be 1 plus beta. You can make beta whatever you want it to be. If we do that, then this expression for the estimate of theta simplifies to alpha h plus beta. So notice the minus 1 and the plus 1 will cancel here. And then we're going to divide this by the alpha h plus the alpha t plus 2 times beta. Okay, so hopefully you can see that the minus 1s are going to get canceled by the plus 1 in the form 1 plus beta, so that our final result looks a little simpler. And this makes a little bit more sense in terms of describing it as the actual data plus our virtual data divided by all of the data, real or virtual, that we've seen. Okay, and to be clear, the difference here, if you compare this to the MLE slides, is simply in adding the virtual data on the end. Okay, you still with me? What do we do for multinomial problems? In other words, problems where we have more than 2 options. It's not heads or tails. It might be 10 topics. It might be 6 sides of a die. For these problems, we will often use the Dirichlet distribution, or Dirichlet. I feel like it's Dirichlet. We can debate about that when I see you on Wednesday. Okay, what is the Dirichlet distribution? Well, it's saying that the joint probability of theta 1, theta 2, and some number of thetas, so I'm going to show up to k, is equal to 1 divided by, we do still have some weird beta function here, of that's a function of an array of virtual counts for each of those k options, times the product from I equals 1 to k of theta I to the beta I minus 1. Okay, and again, just like in the binomial case, think of this beta I as being the virtual data specifically for the parameter theta I. And this first part here, you can think of this as just like a normalization constant. It doesn't really matter where it comes from. Just know that it's some multiplicative factor on the front of this expression. The Dirichlet distribution is often notated as follows. We will say Diri, and then we list the betas. So beta 1, beta 2, and so on and so forth, all the way up to beta k. So if you're going to use this in a problem, this is typically how you would define it, so that people understand what the virtual data you're including is. All right, let's see if we can apply this to the problem we worked on before, which is rolling dice. So let's try this again. We're going to see, can we guess what we roll next? But here, we're looking for the argmax, and that should be an array, over the array theta of the probability of our array of theta values given the data that we've seen, which is proportional by Bayes' rule to the probability of D given our array of theta times the prior probability of the thetas. We don't have a division by probability of D, again, because it has nothing to do with the parameters we're optimizing. So we have our posterior on the left, we have our likelihood on the right, and that gets multiplied by our prior. Let's write out what this expression will be now that we know P of D given theta and P of theta. You can look back at the previous slides to see that. The posterior, the probability of an array of theta given D, is going to be equal to. Now, in our optimization, or in terms of determining the best value of those parameters, we can ignore that normalization constant because it does not depend on our thetas. It only depends on the betas. Now, the hard part. Let's compute the log likelihood. So the likelihood of the array of thetas is going to be equal to, I'm going to simplify the expression already so that we have room on the slides, but all of those exponents, right, log of x to the y is equal to y times log of x. So we can bring the exponents down, alpha 1 plus beta 1 minus 1 times the log of theta 1 plus alpha 2 plus beta 2 minus 1 times the log of theta 2 plus so on and so forth, all the way up to alpha k plus beta k minus 1 times the log of that parameter theta k. Keeping in mind that we could have written this expression as alpha 1 plus beta 1 minus 1 times the log of theta 1 plus the sum of all of the alphas, and let's use like j here, plus the sum of all of the beta j's that don't include the ones. So this will be like from 2, j equals 2 up to k, 2 up to k, minus the minus 1 terms. How many of them do we have? We have k minus 1 of them. Okay, I'm just trying to simplify. Imagine summing all of these other things in parentheses. That's all I'm trying to do there, simplify that. Times the log of 1 minus theta 1. So in other words, we've converted the problem from being multinomial to binomial by saying, well, it's either theta 1 or it's not. Right? We don't care what the other ones are. We don't care to distinguish between the other ones. The reason we do that is so that we can compute the gradient. The gradient is the derivatives. Oh, and actually, I think I should have written these as, partial derivatives. That's my fault. Let me go back real quick. Yeah, all the way back here, pretty sure these should have been partial derivatives. The reason why we use partial derivatives is when we've got more than one variable. So we kind of write this more curly looking d. Okay, so this is the partial derivative of our log likelihood with respect to theta 1. We'd have the same thing all the way down to the partial derivative with respect to theta k. Okay, and this is going to be equal to, I don't know, some crazy expression. Main thing is that if we're trying to maximize this, we're going to set it equal to 0 and solve for the unknown values. So let me demonstrate how we would do that for the first one. So I'm going to solve for theta 1. So the partial derivative of our log likelihood with respect to theta 1 is going to be equal to alpha 1 plus beta 1 minus 1 divided by theta 1 minus this weird sum. So alpha 2 beta 2 minus 1 plus alpha 3 beta 3, alpha 3 plus beta 3 minus 1, all the way up to alpha k plus beta k minus 1. So I'm simplifying the expression, divided by 1 over 1 minus theta 1. That's going to be set equal to 0. Okay, the process is the same. We've done this now. This is like the third or fourth time. You're going to move that negative term to the right side, cross multiply, distribute, gather the like terms. And if you do that, which I would encourage you to do on your own, you should see that the estimate for theta 1 will be equal to alpha 1 plus beta 1 minus 1 divided by a big sum. So alpha 1, beta 1 minus 1, alpha 2 plus beta 2 minus 1, all the way up to alpha k plus beta k minus 1. The principle is the same as before. If we want to do a map estimate for a problem that has multiple options, more than 2, it's simply going to be equal to the number of times we actually see that case in our data, that's the alpha 1, plus the virtual counts of seeing that data, that's the beta, divided by the sum of all the actual data samples and the virtual samples. And again, the -1 terms that are in here are because of how the beta distribution, and in this case the Dirichlet distribution, how those are derived. They involve integrals, and there ends up being this weird -1 in the general form. So some estimate for theta I here would be equal to alpha I plus beta I minus 1 divided by the sum, let's say, of j of all the alpha j's plus the sum of all of the beta j's minus, in this case, k. That k there is because of all the extra -1s that we've got going on. Okay, this is the general form of a map estimate using a Dirichlet distribution. And now I will have pronounced that wrong forever. I hope what you're seeing here is that the -1 and that -k, it's a little bit weird. Okay, so what if we did something similar to the map estimate for the binomial case, where we let all the virtual counts be equal? So typically, our notation for Diri of beta 1, beta 2, all the way up to beta k, we will frequently set this equal to Diri of 1 plus, I'm just going to use beta as a constant here. Notice that they're all 1 plus beta. Okay, instead of having individual beta 1, beta 2 up to beta k, we just set them all to be the same. Okay, and the reason that we're going to do that is because then our estimate for each one of our theta parameters is going to be equal to the alpha I plus, and I'm actually going to show the full derivation here. Beta is now 1 plus beta, right? As we've just literally defined it up here. Each of them is 1 plus beta minus 1 divided by, we've got the sum of the alpha j's, and then we've got the sum of the betas, but those are all going to be 1 plus beta, and then we've subtracted k on the end. So what you should notice here is that in the numerator, that 1 is going to cancel, and in the denominator, I believe this is going to cancel as well, right? The 1 in that sum is going to cancel because there's k of those. It's going to cancel with the minus k. Okay, so the final result here, the map estimate for virtual counts that are equal and set to 1 plus beta is simply equal to, okay, so for those of you who are curious about why we write the Dirichlet distribution as 1 plus something, I think in the homework I define that as alphas, is simply so that that 1 can cancel with the -1 in the equations that we've derived here. So the final result of a map estimate here with virtual counts that are equal is to take the sum of the actual data, alpha I, that we see, plus the virtual counts for that parameter, divided by the total number of samples we actually saw, plus k times beta. That's the total number of virtual samples we have. And that's all there is to it. So let's bring this back to naive Bayes to close things out. Let me remind you that the goal of naive Bayes is that we're trying to maximize the product of some class, let's call it y, that might have one of k options, times, so those were the priors, times the product from I equals 1 to m of a bunch of class conditionals. So this will be like xi, and I'm going to say that that can have potentially one of j options for each of the x's, given y equals yk. Right, I'm writing this in a slightly different form, but I hope you can see the similarities with what we already knew. I'm going to now define these parameters using some different notation. So the prior parameters here, I'm going to define that as pi k. Each of the class conditionals, I'm going to define that as theta ijk. Okay, notice the prior only has one subscript k, and that's because it's only dependent on the class label. The theta has an ijk. I refers to the number of the feature, the index of the feature we care about. J refers to the index of the options of that feature that we care about. And k refers to the class in the class conditional that we currently care about. That's what we're trying to estimate in naive Bayes, all of the pi k's and all of the theta ijk's. We can do this with MLE or MAP. And to be clear, we could use MLE for both of these things. So let me show you what the MLE looks like for these two types of parameters. If we were to estimate pi k, that would equal to the number of instances in our data set where y equals yk. Right? That notation might look a little funny, but let me say it again. That means the number of instances in our data set D such that y equals yk divided by the length of our data set, the number of samples we have. That's the MLE estimate for priors. The MLE estimate for our class conditionals will be equal to the number of instances in our data such that xi equals xij. Notice the first x there is capitalized, second one's supposed to be lowercase, and where y equals yk, divided by, now this time it's not the total number of samples because this is conditioned on the samples of a particular class. So it's the number of times we see in our data set that y equals yk. All right, and then let's do the map estimates. For your priors, you could do this by saying the number of instances in your data set such that y equals yk plus some beta value. I'm going to say that as beta pi. So that's the virtual counts that you care about, divided by the total number of samples of data plus k times beta pi. I'm assuming here that we're adding the same number of virtual counts to all classes. That's a very important note. Okay, if we want to use a map estimate for the class conditionals, those parameters are defined as theta ijk. That will be equal to the number of instances in our data set such that xi equals xij and that y equals yk plus our virtual counts. I'll call that beta theta. Note that's not a multiplication of beta times theta. That's just a single beta term with the subscript theta. And then let's divide that. Again, it's not by the whole length of our data. It's simply conditioned on the number of instances in our data where y equals yk. And then we need to add all of our betas together. Well, if we had k classes, each with an equal number of virtual counts, that would be k times beta sub theta. So this brings together our understanding of Bayes classifiers to completion. In your homework, I am asking you to estimate the priors with MLE and to estimate the class conditionals with MAP. Okay, so these are the most important equations, and this video described how we could derive those using basic calculus. Thanks very much for watching.